Okay, here we are once again. It's the physics video lecture, psci 168, video lecture 18. Okay, I had a lot of queries about homework number 15. So we're going to spend plenty of time on that. This is a central part of the lecture, as I've said before, central part of the course. And if we were together in a room, we'd be spending a lot more time on this and looking at maps and other interesting stuff like that. So let's do this hydropower thing one more time and talk about that homework problem, which will make you guys professional hydropower engineers. Okay. Well, I'll explain as we're going through it why this is such an important problem and what it allows you to do. So we're looking at the hydropower once more, and I will put everything up here in our cartoon because we're referring to this all the time. There's our lake, there's our dam, we've got the penstock, goes all the way down to the powerhouse, and the lower lake there, I'll just write power. And so we have between these two water lines this important elevation difference H between the lower and the upper lake. So put a little color in there while we're on the topic. Okay. So there's our lake. Here's our lower lake. And in fact, we can put the mountains back here, and if I don't forget, we can discuss the significance of that as well. We know we're sending out power cross country, but we also know we can receive power here from some coal or gas-fired power plant. Maybe it has put two smokestacks on it this time. Okay. So yeah, we can send power, over to the civilization, but we can also get power from here to do our pump storage. Good, and I'll put the formulas here. The potential energy, we'll call it W, is just the mass of the water, G times H. We have the power formula, M over T GH, seemingly the same thing, but not quite. And we have the fact that power, once again, P equals energy divided by time. Now this is the one we can invert and write down in three different ways. We can say work is power times time. We can say time is work divided by power. So we've used all three of those. Good. So let's keep going. Anything else here? Yeah, we know what's going on in there. We've got our water cycle and all manner of good things. Yeah. How about this? We've got the incoming solar radiation, and it drives our water cycle. Okay, and so forth. So let's look at that numerical problem. Let's set this up here. So the numerical, that is to say the homework problem, we had a reservoir and I'll write the volume equals the length times the width times the depth, and I had 2,000, 1,000, and 50, so 2,000 meters times 1,000 meters times 50 meters. And what else did I put? I'll put the whole homework problem up there. We had H was equal to 500 meters find potential energy in joules and in kilowatt hours. And then we had a flow rate. The flow rate, so I'll just write down flow rate. We took 20,000 kilograms per second. Turns out, you'll see in the final answers, these are all really good, realistic, reasonable numbers. Find the power P and time T to empty the reservoir. I'll just write to empty the lake. Okay. So now we have everything here. So let's go ahead and work these out. First of all, I'll keep going here in red. This one here, we have 2 times 10 to the third times 1 times 10 to the third times 5 times 10. So this is a great place to use our scientific notation. We have 2 times 10 to the third, 1 times 10 to the third, 5 times 10 squared. So what do we have here? 10 to the third, 4, 5, 6, 7, 10 to the 3, 4, 5, 6, 7, 8, and 2 times 5, that gives us 9. Okay. Oh, you know what? I better make sure I... 10 to the 1, 3, 4, 5, 6, 7. Therefore, that would be 3, 6, 7 times 10 would be 10 to the 8 cubic meters. Okay, so we have 10 to the 8 cubic meters. Now, the mass, you know, I see that I didn't assign it quite that way. No problem. Okay, so let's go under here. I want to have everything on the board at once. Okay, let's see how we can do. But we will use this number. So now the mass, I'll use capital M, is the density times the volume. Okay, so just keep doing this here. Let's write density. Density of water equals 1,000 kilograms per cubic meter. Okay. So for our mass, which is what we wanted, we have 10 to the third kilograms per cubic meter. Oh, we're in no hurry here. 10 to the third kilograms per cubic meter. And then the volume is times 10 to the 8 meters cubed. Units are good to write out. The meters cubed cancels, and we have 10 to the 3 plus 8. So that's 10 to the 11 kilograms. So that was the first part of the problem. Okay, we wanted to find that mass, and now we have found it. 10 to the 8 kilograms. Okay. So what was next? We want to find the energy. Okay. So next, find energy. Find energy, which is to say potential energy. We use these things interchangeably. But we know that is M times G times H. We're using our capital M right here. So this potential energy, capital W, is equal to 10 to the 11 kilograms times 9.8 meters per second squared, and then we were going to have 500 meters, as I recall. Yes, 500 meters. So in our picture up there, the H is 500 meters, and I should point out that is the level between Courtright and Wishon dams, okay, or reservoirs. It's about 500 meters. So it is a really realistic example. Yeah, we have 10 to the 11. You can see what we're roughly going to have. 10 to the 11, roughly 10 to the 12, 13, 14. So it's going to be about 5 times 10 to the 14. And the actual number is going to be 4.9 times 10 to the 14 joules. Good. So we get 4.9 times 10 to the 14 joules. Now here, it gets interesting because you can have this number in joules, we just, MGH, and you could do a conversion, because we know that 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. So this is essentially multiplying my equation by 1, okay? Kilowatt hours, and the joules are going to cancel. So I'm dividing that 4.9 times 10 to the 14 is being divided by 3.6 times 10 to the 6. Well, you can immediately see 4.9 divided by 3.6 is a little more than 1, and 10 to the 14 minus 6 is 10 to the 8. So even if we didn't have a calculator, we'd be fine. I went ahead and put it out there, and I have 1.36 times 10 to the 8 kilowatt hours. Wish I had a little more room here. I'll put it underneath here. 1.36 times 10 to the 8 kilowatt hours. So that's 136 million kilowatt hours. Anything else there? Yeah, I wanted to make a point about that as well. 6 times 10 to the 8 kilowatt hours. Yeah, so make sure you get all of these things down as clearly as you can. Because we can stop and think about this for a moment. Go ahead and add up all of the kilowatt hours in your household, say over the course of a year. Okay. And then you can figure out how many households could be served by this dam. What we're going to find out is, at the rate that it is going to empty later on in the problem, it lasts a couple of months, you can do a calculation that with those couple of months. But here you actually have a number. This lake holds that many kilowatt hours worth of energy, and you can compare to how many households of your type could be served by it, just by dividing by your yearly use. Okay, so you're already getting at something that you had no idea of before this semester, that you can just take these kind of data here and figure out the energy needs of civilization. Okay. And that's why I think this section of our course is so central, because there's no difficult mathematics involved. The physics is not difficult either. There's some level of sophistication in all of this energy discussion, but it's also very basic. So I'll make another point. This number here is a maximum value. We're never going to get all of that energy because there are losses and inefficiencies in the entire chain from starting in the lake to getting it into our houses. But this is this is a maximum number that represents a law of nature. Okay? Maximum amount of energy available in that elevated body of water. Okay, so that's good. We're going to leave that up there. And what else was in that problem? Then we wanted the power. So we're going to use the power formula. I'll go ahead and erase this picture, but you know, I need to have that dam there in place for the further discussion. May have to redraw it. So next we have power. Power is M over T GH. So this time we're going to take the 20,000, that's 2 times 10 to the 4 kilograms per second. And again, I said that represented 20 cubic meters. This is a meter on the side, okay. 20 cubic meters per second. Okay. And this machinery we're talking about is definitely big enough to do that. These penstocks are huge. Okay, so 2 times 10 to the 4 kilograms per second. Then we've got the 9.8 meters per second squared. We have the 500 meters. Now, as long as you use kilograms, meters, and seconds, all of our formulas come out with the correct units. In this case, it's joules per second, which is watts. Okay. So if we look at this multiplication, 2 times 5 is 10. Okay. And that'll be 10 to the 1, 2, 3, and 4 will be 7. 9.8 times 10 to the 7. Okay. So we have 9.8 times 10 to the 7 watts, which is almost 10 to the 8 watts, which is almost 100 million watts, okay? 100 megawatts. So you notice these numbers are big, but that's what's actually out there in the world. And as long as we have our scientific notation, powers of 10, these things cause us no problem at all. So definitely try to always go to scientific notation to understand whatever you calculate. So there's our power. Okay. And you could also say, well, what's the average power consumption of a household? And then you could say how many households can be served by this many watts as well. That would be another type of calculation. To find the average power of your household, you would take your kilowatt hours per, say, day on average, or month, and divide by that many days. And then you would have a constant kilowatts, okay? And then you could compare your kilowatts, which is 10 to the 3rd watts, to this 10 to the 8 roughly, and see how many households could be served. Okay, the final question was, I think I have some room here. Important one. I'm going to send this up. We're always using, you know, these formulas here. We just used this one, calculated the energy with that one. Okay. Of course, we calculated the mass with this density times volume. So this is an important one too. We could even, you know, put it up there in that list. So the final one we want to calculate is the time it takes to run out. So I'm going to use a little more space just to get my point across. Okay, so now we're talking about this last formula here. Power is work over time. Power is energy over time. We can write this equation in 3 different ways. Power, that's its definition, energy divided by time. Or we can solve for W, for the energy is equal to power times time. We used this when we defined the kilowatt hour. We said we had 1,000 watts times 3,600 seconds. So that's where the kilowatt hour came from. And we can also take this equation and solve it for T. And there the time is equal to the energy divided by the power. So yeah, you're getting a lot out of this basic definition here. And this is the one we're going to use, okay? So how long is this system here going to run, okay? It has a certain amount of energy. Due to this flow rate, there's a certain amount of power, and if we divide that energy by that power, we're going to get the time in seconds, because our consistent units, everything is kilograms, meters, seconds, okay? So the time is going to come out in seconds, and we'll just plug in what we had there. So for the energy, we have the 4.9 times 10 to the 14 joules. Okay. Remember, the joules is the newtons times the meters. That has all the kilograms and seconds and stuff. So you can't use the kilowatt hours right here. You're going to use the joules. And the power was what we just had there as the 9.8 times 10 to the 7. 9.8 times 10 to the 7. Okay. Joules per second. So the watts are joules per second. Now this fraction, you're going to get the cancellation of the joules, and the seconds are going to end up in the numerator. Okay. So 4.9 divided by 9.8 is a half. 10 to the 14 minus 7, so 10 to the 7, and a half that 10 to the 7 would be 0.5 times 10 to the 7, okay? So I have 0.5 10 to the 7, 5 times 10 to the 6 seconds, okay, fantastic. 5 times 10 to the 6 seconds. Now how many seconds is that? That's a lot. How many days is that? Maybe that's a better question. So we can write is 1 day divided by 24 hours, which is 3,600 seconds. Okay, so this is a conversion again. Right, 1 day equals 24 hours, and 24 hours is 3,600 seconds. So that will be 58 days. 58 days, which is just about 2 months. Okay. Anything else here? So I have 6, 4. That'll work. 58 days. Okay, I'm going to check the time. Okay, good. So this is a really complete type of problem, and I want to make a few more comments on it, because if you have this, you can make up your own numbers, but you could also discover the hydroelectric potential of any place at all. And so I want to mention 2 things in hydropower. What should we title this here? Hydropower planning. How about that? Or I'll give this a different title. Yeah, well, that's a good title. Hydropower plans. Let's look at 2 aspects of this. The first aspect is in surveying the land. Okay. This is where I would like to have us all together with a bunch of maps spread out across a big table where we could learn these things. So surveying the land and maps. So there are different types of maps that give elevations in particular contour data. So maps, I'm talking about topographic maps in particular. Some of you may know how to read topographic maps and it'd be nice to be together and doing that. What you can do with a topographic map, you know, say you're looking on your map here, here's your map, and there's a valley, and there's a mountain and there's a valley, so the mountain's gonna have these kind of contours, and the valley around it is gonna have some really steep sides. Well, I may send you guys some images of topographic maps that we can look into. This is not a good picture. Point is from the topographic map data, you can actually estimate the volume of a valley. Okay. So the two things we can do here, we can estimate the volume of a valley, and remember the volume was part of our problem, right? We had the volume of that lake. So we can estimate that from a map. And the second thing you have, we have the little stars there, is the elevation and the relative elevations. You got those elevations with Google Earth, okay, Google Maps, whatever you used. So you can get elevations. For example, the elevation of this valley above some canyon bottom where you could put your second dam. And so these kind of calculations, where I gave you those numbers, 2,000 by 1,000 by 50, you could come up with those same types of numbers using a topographic map. Okay. So surveying the land, you got the maps, you got the locations, and therefore you can then calculate the potential energy just the way we did. Another interesting aspect is snow surveys. So the mountains here, say, are covered with snow in the winter. People go out and measure the snow depths and estimate the amount of water that's going to be available to flow into the reservoir. And they get rough estimates of when it's going to be there and how long it's going to last. So that's all the long-range planning. So in addition to the energy availability that's going to be based on the water, of course, the irrigation potential as well. And it'll be released down here and then eventually end up in the Central Valley in agriculture. So yeah, it's a rich subject, but this particular problem allowed us to just get the key quantities, okay? The potential energy that is available. If you do your snow survey, you know even more about that. And then based on how much it's released here, right? The flow rate, based on the flow rate, you can talk about the power of, that can be generated, and based on the flow rate, you can get the time. That was the last thing we got, the time, how long it's going to flow for. Okay, good. So I'm glad people asked me. I had a number of people who emailed and wanted to have this problem discussed. So actually I'm glad it came up, and if you have any other questions on homework, you can always ask me in the emails, and I'll be glad to talk about them up here. Okay, now we want to move on. Yeah, perfect. So we're moving on to our next topic. Is a major study that's going to take a few weeks, and that is thermal physics. So thermal physics. And we're going to do this thoroughly enough so that we have all the necessary principles. And I'm going to start with something and then do a detour that I just planned, just thought about doing today. But thermal physics, we're literally starting with the sensation of hot versus cold. That's how basic we're going to start out again. Okay? Just like we started out, talking about the hunt on the very beginning of this class, and then talking about systematic thought, developing the need for geometry and so forth. We're going to start with the sensation of hot and cold, and we're going to associate heat, hot, with fire, and cold, say with cold water or snow or ice. Okay. And we're going to make our way through temperature scales and thermometers and everything. We're going to do it really systematically until we get to be able to know how much energy there is in a certain quantity of some burnable substance. And we're going to need the thermal physics to talk about solar energy, so this is very central. However, so I came to this fire concept, and I realized we're having a lot of wildfires in California right now. So I decided to show you something about fires and fuel. So next, let's just call this fuel loads in California forests. And I have an interesting book that I'll show you some pictures out of, and I think we have enough time to do this. Let's see here. Yeah, this will be perfect. So fuel loads in California forests. Okay, the fires this year have been extraordinary, extraordinary. And I brought a book here, and instead of holding these pictures by hand like I did last time, I'm going to prop them up, and hopefully you guys can get better screenshots. Fantastic. Okay, that's completely in the picture. That book, maybe I'll point with a pen. So this book is called Fire in Sierra Nevada Forests. Make sure you get a screenshot of this thing, because you may be interested in having a closer look. I'm going to show you guys a few pictures out of it. By a biologist, forestry guy named George Gruelle. And even in this cover picture, you can see he's analyzing historical photos. And the interesting aspect of his project is that the historical photos can be tracked down, and one can find the exact location where the historical photo was taken and take the contemporary photo. So the cover already shows Yosemite Valley, and I'm going to go through a number of pages that I singled out for you guys to see. And I'll just recommend that you get screenshots of all these things, print out what you find interesting. By showing you that book, you can always go for the whole thing. It has hundreds of pictures. So that's Yosemite. Now I'm going to go to the way the rest of the book is done. Okay. First we gotta see if we can tilt this up successfully. There we go. Perfect. Okay, maybe a little over here. Good. So what we have here is picture on the left, 1899. Picture on the right, 1961, and the little inset is 1994. And what's being shown is that there is enormously more forest cover in those 150 years. Actually, those, yeah, not even 150 years on this. Some of them are that old. So that's the project. He locates the exact spot where the picture was taken and takes it years later. And you can see the increased forest cover. So I'll show another one. So you want to get screenshots of all of these that you can. This one is, let's see here, hey. Looking down canyon towards El Capitan from a different spot in Yosemite Valley. And the left one is 1866 and the right one is 1961. The inset is 1994. A current picture would be even more densely wooded than we see in those pictures. So that was this one. Another good screenshot. I have just a couple more of these. This one shows the technique of Mr. Gruelle in interesting fashion here. Let's see if that's good enough to screenshot. Got a problem there. Okay, hope it stays. Yes, so the technique he used is to locate the same rock. So the picture on the left is 1910, the picture on the right is 1995. The rocks in both pictures are clearly identical, and you can see how much more wood there is in the right picture. This one in particular is interesting because you can see that the tree trunks on the left are bare for about 5 feet or so, 5 or 6 feet they're bare. And that's because, and this is the part of the point of the book, the natural fires that sweep through the woods in a state of nature without any fires being extinguished. Those natural fires will burn the bases of the trees and all the little twigs without actually damaging the trees. So George Gruelle, the author of this book, and the guy who did the whole project, tracked down about 100 of these historical photos, and it's one of the most convincing presentations I've ever seen. Wanted to make sure everybody sees it. So the theme here is fuel loads in California forests. Out of the other 100 or so, I have one more that I'll show you. Make sure you get screenshots of all of these. This one is taken on the east side of the Sierra Nevada. That's a place I've been. So the point on this one here, this is Lee Vining Canyon. And you can see again the rock that the author located. On the right bottom corner of the picture, it's the same rock. Okay, let's try that again. It's all one take, no edit in this class. Okay, let's set this up and hope for the best. Once again. Okay, good. Yeah, you see the same rock, so that's how you get the location. And then you see the enormously increased forest cover between 1885 and 1995. Okay, so that's what I wanted to show you guys. And I will pull this out of the way. And check our time. So I think we had enough time. We're running on 40 minutes. So for the homework, well, make sure you understand this calculation. If you didn't understand it before, you do some examples of your own if you're so inclined. And then for the notes, go ahead and include as many screenshots as you found interesting. And I gave you the cover of the book just in case you want to look that up and do a little more research. Okay, so we're just getting into thermal physics. We did a little detour into fuel loads because it's a current event. But next time we'll get into hot, cold, temperature, and very systematically make our way up into everything we need to get to heat engines and beyond. Good. See you next time.